Morning, student. This is Mr. Teo again. In the last lesson, we talked about the effect of damping ratio and undamped natural frequency on the whole second order response. We look at the damping ratio zeta per se in for the case of zeta equals 0, which is the undamped case. The output signal will be freely oscillating at omega n. And then we look at the damping ratio that is between 0 and less than 1. We call it the underdamped case, whereby there is some peaking, and over time it will damp down to a steady state value of k. And then also we proceed to look at the critically damped case, which is zeta equals to 1. And for that case, there is a gradual rise until it hits the final steady state value. Also, we look at the case whereby zeta is greater than 1, whereby of course it takes even a longer time to hit the steady state value k. Now we also look at the importance of the parameters of omega n and zeta on the overall response, and especially for the case of underdamped, it is mainly used to compute all the timing response, like the maximum peak, rise time, delay time, peak time, settling time, etc., etc. So today we are going to continue the quest of learning on the second order system by further extending our knowledge into the steady states response and steady states error for first order and second order. And then after that, we will look at the system identification for two types of system. One of them is the first order plus date time self-regulating system, and the other one is the first order plus date time integrating system. Okay, without further ado, let me just go into the transparency of the slides.
Now let's look at the steady states of a system. When we look at the steady states of anything, usually we will give it a rather long time to let it settle down to its steady states. Here it is the same. When we talk about steady states of a system, we will wait for a long time, meaning t approaches infinity. Remember that time is 1 over frequency. Hence when time approaches infinity, meaning frequency will approaches 0. So to find the steady states of a system, if we are working in the time domain, we will let t approach infinity and see what happens to the expression when t equal infinity. On the other hand, the same result can be yielded when we work in the frequency domain, and that is the S domain. But this time we must multiply the frequency domain expression by S and let S tends to 0. This is what we call the final value theorem that you have studied in your year 1 or 2 mathematics. If we do the final value theorem on the first order system, that is k over tau s plus 1, then we need to multiply the first order equation by is and take the limit for s to approach 0. Bringing x, s, which is the input unit step function, over to right-hand side of the equation. We will have s term cancel with 1 over s. If we set s equals to 0, the final result is the steady state response for first order system is k.
Okay, this is a very long explanation, but by and large what it's trying to say is, if I have a step response for the input, then of course for the first order response at the output, we expect the signals goes this way, as we have seen before in the first order equation, and the first order expression will be k over tau s plus 1, as we have did it in the previous few chapter. Right now, in this portion, we are going to study the steady state response. That means the k value. Right now, why the steady state response? Now, how to compute the steady state response? Now, when we say steady states, it means that something has already settled down and waited for quite a long while. Now, take for example, if you have a boyfriend or girlfriend, you don't immediately go steady with the boyfriend or girlfriend. It will take some time for you to get steady. And basically, the longer time you wait, the better you can confirm that it is really a steady state. Now, so therefore, for anything to be in steady states, time has to approach infinity. Now, if times approach infinity, frequency being the inverse of time, so if time approach infinity, frequency will have to approach 0, right? Now, S is actually 2 pi f, right? J omega, S is actually J omega, which is J 2 pi f. Now, if f approach infinity, then S would also approach to 0, right? So that is, so it's straightforward. So now, so therefore, we have actually been working on the time domain and the Laplace domain. So there is a theorem that you studied in the year 1 and year 2, which is called the final value theorem. Now, if we look at a function in the time domain, which is called f of t, then the steady state value will be t approach infinity. But if you look at it in the S domain, which is the frequency domain, then you have to take the f of s multiplied by s. Then you take the limit of s approach to 0, and that is basically the final value theorem. Now, if we do the use the final value theorem and put it to the first order system, basically the first order system will be replaced by k over tau s plus 1, right? So again, there is a s that is plugged into here because of the final value theorem equation. Now, if we put the x of s, which is the input, to the right hand side, and assuming that the x of s is actually a unit step function 1 over s, so you can cancel the s with the s that is prior to this k tau s plus 1. So by cancelling, you are left with this case. Now, if you let s tends to 0, meaning that this term here will disappear. So finally, the value will be k over 1, which is the final value will be k. That's why in the previous chapter, we always talk about output response settling to k. And for first order system, it actually really settled to k. Okay.
In steady states response, we look at how output y, s, settle as time approaches infinity. However, for steady states error, we look at how error e, s, settles when time approaches infinity. The final value theorem used is still the same, except for the expression used. In previous steady states response, we use y, s. Now we use e, s. E, s, over u, s, is always equals to 1 over 1 plus g, s, multiply by h, s. Same thing, we need to multiply this expression by is an input unit step function 1 over s. Simplifying, we will get 1 over 1 plus k when we set s equals to 0. Hence the steady states error for first order system will tend to approximately 1 over k if k is much greater than 1.
Now, in the previous slide, we talked about the steady states output, that is y settling when you wait for a very long time. Now, for this second slide, we talk about steady states error, which is instead of looking at the output, we look at the error here, and we say, when does the error settle down? Because if the output settled, then the error must have settled, right? So this error must have settled to certain value. So the error basically here will be actually equals to the input minus by your output, right? Then that's the error. Input minus by output, right? So input minus by output, then this will be the error, right? The steady states error. Now, steady states error can be proven to be of this expression. E of s over u of s. That means error over input will be equals to 1 over g of s, h of s. Okay, if you are keen in going through the mathematics, you can go through this chunk of mathematics here. Now, if you cannot understand or think that this is too tough for you, you can just remember this. Now, how to remember this guy? Now, remember for closed loop negative feedback transfer function, if you remember block diagram manipulation rule 7, it states that if let's say we want to find y of s over u of s, it is basically what? It is basically g over 1 plus gh, right? G over 1 plus gh. But if you want to move from y to E, you are actually moving backward, right? So you have to divide by G. So for G over 1 plus GH divided by G, basically you get 1 over 1 plus GH. And that's how you remember for E of S. The expression is 1 over 1 plus GH. That means the whole G over 1 plus GH expression, you divide by G, then you get 1 here. Okay? So that's how you can remember it. Huh? Now, so again, using the same final value theorem that we have used in the previous slide, we put the steady state error as the limit of S as S approach to 0 and multiply by S, and then of course plus the error function. Error function is given by 1 over 1 plus GH, right? Now, of course, we will bring the input U of S to the right hand side and it cancels with the S, right? So basically very straightforward. Now G of S we will substitute by K over tau S plus 1, right? K over tau S plus 1. But H of S, because it's a unit feedback, we will just use 1. Okay, so with that, as S approach to 0, what happens to your tau S? S will be 0. So it's actually 1 over 1 plus K. Now ignore the KP, it's just a K, right? So basically, you would have 1 over 1 plus K. But for K value, which is very much bigger than 1, you can say that it is approximately equals to 1 over K. So for a first order system, usually, if you wait long enough, the gain will settle around 1 over K. Okay? The steady state error will settle around to 1 over K.
Now let's take a look at example 4, where we attempt to convert an expression in the S domain to the time domain with the help of Laplace table. In the formula sheet, for C, S over U, S equals to 2 over S plus 0.1, we can bring U, S, to the right-hand side of the equation. Substituting U, S, equals to 3 over S as given in the question, we yield C, S, equals 2 over S plus 0.1 multiplied by 3 over S. Next we need to do a partial fraction by letting 6 over S bracket S plus 0.1 equals to A over S plus B over S plus 0.1. Rewriting the next steps by making all denominator equals to S bracket S plus 0.1. The numerator will change accordingly to maintain the same expression. Since now all the denominator are the same, then all the numerator must equals each other. Meaning we can write 6 equals A bracket S plus 0.1 close bracket plus BS. Substitute S equals minus 0.1 and 0, we will yield A equals 60 and B equals minus 60. Substituting A and B value back to the expression, we have C, S, equals 60 over S minus 60 over S plus 0.1. Taking a Laplace inverse yields C, T equals 60 bracket 1 minus exponent minus 0.1 T.
Now this is a example 4 of bringing your expression from the Laplace domain, which is the frequency domain, back into the time domain, right? And then it is given also that the expression for the output over input is given by 2 over S plus 0.1, right? And the input also is given as 3 over S, which is the 3 unit, not unit, is 3 unit step function. So 3 volt step function, right? So basically, if you plug in, first of all, if you want to find C of t, which is the time domain equivalent of C, you first have to find what is C of S. Now C of S, you have to bring your U of S over, right? The input over to this side. So by bringing the input towards to the right hand side, you basically can plug in the 3 over S and you multiply them together, you get 6 over S plus 0.1. Now, in order to do the Laplace transform, or rather the Laplace inverse, first of all, we got to separate them into 2 terms by using partial fraction. So using partial fraction, as you have did in your mathematics, first of all, you got to equate this. We let 6 over S plus 0.1 equals to A over S plus by B over S plus 0.1. Now with that, on the right hand side, we can common the factor, meaning that the common factor will be this multiple of these 2. Then of course, if you multiply these 2 together, you got to make sure the top is also multiplied by the same thing, so that if you cancel out, they are the same as A over S for the first term. Likewise, for the second term, this guy is leg of S, so you multiply here by S, but multiply on top by S. So if you cancel out, they are still the same. So we never change anything. Now, take a look at this row. Basically, the denominator all are the same, right? If the denominator all are the same, which means that I can just put this guy add with this guy over the entire denominator, which is the same thing, right? So if this is the case, then the input, the numerator 6 must equals to the denominator, the numerator on the right hand side, which is A bracket S plus 0.1, close bracket plus by BS. So this is your new term that you have come out with. Now, with this term, if we substitute S equals to minus 0.1 for the first case. So when S equals to minus 0.1, the whole A term equals to 0. So your B will be minus 0.1 times B, right? Minus 0.1 times B, you divide by, you bring this minus 0.1 over to here, you will be divided by 6 divided by 0.1, minus 0.1, you get minus 60. So B, you get minus 60, right? Now for the second case, if you set S equals to 0, so this guy will be equal to 0, then you have 0.1 A multiplied by, this is 0, right? Because your S is 0. So it's 0.1 A, so you bring the 0.1 over, A becomes 60, right? So after you solve for this, you can basically put back this minus 60 and 60 into the same expression that we started off, and you get this expression in Y of S, right? So you can group the common factor, and then of course you do a Laplace inverse. Now remember, in Laplace constant, we can bring it out, and basically if you take a Laplace inverse for 1 over S is 1, and then of course for 1 over S plus 0.1, you get e to the power minus 0.1 t. And that's basically it. Basically, for this step to this step from S domain to time domain, if you are not very confident, you can refer to the formula sheet that is provided in the tutorial session. And in fact, the formula sheets are able to be referred during your test. Right?
Similar to steady state response for first order system, the same methodology is used to find the steady state response for second order system. Only changes the transfer function, where we replace the first order generic transfer function by the second order generic transfer function. The rest of multiplying by S and bringing S, which is a unit step input, to the right hand side, and finally setting S equals to 0, is all the same. For the second order, we realize that the steady state's response will approach K given long enough time.
Now, just now we just investigated the first order, both the steady state response and the steady state error. Now we are going to proceed with the steady state response of the second order. Now, steady state response, we look at the most complicated one, which is the underdamped case. You will settle down at this value, which is what we call the steady state response at this point. Now, of course, if we use a second order, then our generic equation will have to change from K tau over S plus 1, tau S plus 1 to K omega n squared over S squared plus 2 zeta omega n S plus omega n squared. So this is a generic equation for your second order transfer function, right? So again, using the same method or way of doing, we need to shift the input to the right hand side and then replace the input by 1 over S, and then you can cancel out this S, right? Now, and then the next thing we do, we put S to 0. So if S equals to 0, S squared term must goes to 0, and this 2 zeta omega n term must goes to 0. So what happens is you have K omega n squared divided by omega n squared. So if you cancel the omega n squared with the omega n squared at the numerator and denominator, you get K. So that's why in the final value of this tends to a K value, right?
Similarly, for steady state's error, replace the E, S, with the error for second order generic equation using 1 over 1 plus G, S, H, S, and do the same analysis. Finally, you will notice that the steady state's error will approach 1 over K. If K is much greater than 1.
Also, this is for the steady state error, which is here. And remember, the steady state error is given by this general equation called E of S over U of S. That means error divided by input is 1 over 1 plus GH, right? So using this same equation, we know G is basically your generic equation. H is basically 1. Now, if you do it in this fashion, then your E of S must be equals to this case, right? And then, of course, multiply by the unit step function, which is the input. Now, if you put this in together with the unit step input, then again, the cancellation can occur. And then by setting S equals to 0, meaning your S squared term and S term will disappear at the denominator, leaving your omega n squared. So they will cancel out each other. So basically, your whole expression will become 1 over 1 plus k, right? Because the whole term will become 1 if you solve this, right? Now, with this, you would say that, again, the same thing. If k value is much, much bigger, then the steady state error will tend to 1 over k, which is similar to the case of the first order system.
So far, our analysis for second-order system steady-state error is only using unit step input. Now with other type of input like parabola or ramp, the steady-state error also changes. Also, if the system type is changed, the result of the steady-state's error will change. For order, we look also at the denominator. The power of S with roots at 0.
This table tries to show you that because just now or so far we have been talking about just the step function, right? But the input can be other than the step function. It can be ramp, it can be parabola, it can be any function, right? Of course, for simplicity's sake and for discussion at our level or at the poly level, we won't complicate the matter by introducing you the ramp function or the parabola function, right? However, sometimes we may also include the ramp function in the lab, but of course not parabola. So steps and ramp function input possible. But for the order, the system type, usually we will be looking at maybe type of 0 or type of 1. Type of 2, we seldom. So basically, it's just limited to type 0 and type 1 in terms of calculation. In tutorial, we'll just do that. But if you type 2 and type 3, then it will get more and more complicated. But what it's trying to say here, if I vary the input response and I vary the type, then your steady state error may change in terms of expression. For example, in this case here, it will be 0. And in some case here, it will have a certain function, right? Like a over 1 plus k or a over k, a over k. And then for the other situation, it will be infinity, right? So that is the difference in terms of steady state error table that is being plotted out, and let you have a bird eye view of how the response will change.
Now let's take a look at example 6, which will give us a better idea of what is order, type and steady state error. Given G, S0 which is equals to Y, S, over U, S, and also equals to K bracket S plus 5 over bracket S plus 7 bracket S plus 3. Note, even though we cannot see S at roots 0, S to the power of 0 is 1. Hence the type is 0. Also, if you expand the denominator, the highest power will be S to the power of 2. Hence the order is 2. For steady state error, we must work out the expression for 1 over 1 plus G's H's. As we already know, S equals to 1 over S will cancel with the S term in the limit theorem. Thereafter we set S equals to 0. Resulting steady state error in term of k to be 1 over 1 plus 5k over 21. Equating to 0.1, resulting k equals 37.8.
Now this is another example that tries to show you basically what is the order of the system and what is the type of the system. And at the same time, it also tried to formulate a steady state error by you having to determine what is the k value so as to have a steady state error of 10%, right? So to start off, of course, if you want to look at the order and type, again, we are always interested in the denominator, right? So for the order is very straightforward. You just multiply the S term with S term, and the maximum S power will be S squared, right? So S squared, since it's 2 on top of here, therefore the order will be the second order equation at the bottom, right? With the second order, then of course the order will be 2. Now, for type, we always look at the poles at the origin. That means this can be actually written as s plus 0, right? S plus 0 bracket raised to the power of 0. Now, s plus 0 is equivalent to s. So s raised to the power of 0 is anything raised to the power of 0 will be 1, right? So therefore, if you see no s, it's actually s raised to the power of 0. So s raised to the power of 0 is equal to 1. Therefore, the type must be, because the power is 0, therefore the type must be 0. Okay, as simple as that. Now, for the steady state error, we again must apply the limit theorems, and we know that the error will be 1 over 1 plus GH, right? And then if you bring the input step function over to the right-hand side, again, you have the S term cancelled with 1 over S term, right? And if you plug in the expression here, and of course, assuming unit step function, unit feedback, our H will be 1, so it's multiplied by 1. Now, if you set the S to approach to 0 or equals to 0, then you will replace all the S term by 0. Then you will result in 1 over 1 plus 5k over 21, right? With 1 over 1 plus 5k over 21, and then we know that the steady state error is given to be 10%. So 10% is 10 over 100, so it's 0.1, right? So with this expression, if you just solve it, simplify it, you will get k equals to 37.8, right?
For example 7, splitting C's terms into summation of few terms using partial fraction. Thereafter finding the coefficient of A, B and C by letting S equals to each of the roots.
Now, another example, which is example 7, basically it requires also partial fraction, and then Laplace inverse, and then of course a steady state response. Now, of course, it starts off by giving you the output over input relationship, which is given by 3 over s squared plus 2s plus 3. And then it gives you the input expression is 1 over s. So doing the same routine work, we need to find what is C of s. C of s will be this term multiplied by U of s. So U of s, we substitute in as 1 over s. So as a result, you would have 3 over s bracket s squared plus 2s plus 3, right? So now you need to do a partial fraction to split the two terms. So you have a over s, bs plus c. Because this is a quadratic equation, you have the bs plus c, s squared plus 2s plus 3, right? Now, again, trying to common the denominator, you have s times by this term, s times by this term. Of course, on top it must be times by the same term. And then if you try to cancel out, this will be still a over s, so it's equivalent to the on top. Now, this guy is lack of s term, you multiply the bottom by s, and the top also you multiply by s. If you cancel away these two s, it's still equivalent to the top. So we never change anything. We just rewrite, make sure that all of them have the same denominator. Now, with that, right? So basically, we can combine the denominator together, and you will be sure that 3 is actually equals. If the denominators are the same, that means the numerator must be equal, right? So that means 3 must be equals to this thing. 3 is equals to this thing. So by doing so, if we set s equals to 0, then a will be s equals to 0. So this one 0, this one 0 will be 3, right? 3a, right? And then 0 will be this one 0 and this one 0. So this whole term will disappear, right? So 3a equals to 3, then a must be equals to 1, right? Oh, so as simple as that. Now, if you, after you plug in the a equals to 1, then you can do a coefficient comparison. So you have c, if left-hand side equals to 3, right-hand side already equals to 3, then these two terms must be equals to 0. Now, if c plus 2 equals to 0, then c must be minus 2, right? Then also, if this guy, b plus 1 equals to 0, then b must be equals to minus 1. So that's how you get ABC. To calculate out the coefficient for A, B, and C.
Finally, by taking Laplace inverse using the Laplace table in the formula sheet to get the time domain equivalent.
Now, of course, once you split the term is 1 over s, you substitute A is equals to 1, then B is also equals to minus 1, and C is -2. So therefore, I take out minus, I put a minus here. So it's S plus 2. So you can see that the whole expression is changed into this form. Now, of course, the next stage is we try to manipulate it to such that it equates close to this. So you just change the top. S plus 1 is actually, S plus 2 is actually S plus 1 plus 1, right? And then below is S plus 1 squared plus 2. You get this term, right? By doing so, then you can change it again further to two terms. One of them is S plus 1, one of them on top is 1. So by again re-manipulating this whole thing, this is square root of 2 squared, right? It's still the same as square root of 2. And then with this form and this form, basically you would result in, the first one will be result in EA AT cos omega t. That's why you have EA AT cos omega t. This guy changing into this, right? And the second one will be omega over something squared plus another omega squared, right? So this will be result into this one, right? And of course, the omega will be root 2, right? So you have a 1 over omega here, because this one have a omega 1 over, this is omega, right? So therefore you can convert into this form. But this sounds a little bit complicated, and it takes some experience to really know how to rearrange these guys into this form to coincide with the Laplace table and to get this. So of course, rest assured that the test and exam, I will not set something that kind of difficulty level. But of course, for the sake of studying, we need to have the knowledge that it is possible to convert the Laplace expression into cos and sine function. And that's the purpose of this example. Okay?
To find the transient parameter like rise time and settling time, we must first be able to find omega n and zeta. This is easily obtained by comparing 3 over s squared plus 2s plus 3 with the second-order generic transfer function. Upon comparing the coefficient at the denominator, we straightaway will be able to deduce omega n equals to square root of 3 and zeta equals to 0.5774, which is underdamp. Using the formula found in formula sheet for rise and settling time, we can calculate and confirm rise time equals 1.55 seconds and settling time equals 4 seconds.
Now, of course, continuing the solving the question, the last part is to ask you to find the rise time and settling time. Now, of course, to find the rise time and settling time, first of all, you need to find what is zeta and omega n. Remember, in the previous chapter, we say that so long as you know zeta and omega n, it is very easy for you to know any of the timing parameters, right? Now, in order to find the zeta and omega n, first of all, you got to take the closed loop transfer function and then put it side by side with the generic equation and basically do a comparison at the denominator. Now, please take note, for every single term, whether it's the S squared term, S term, and the non-S term, they must exactly equal, be able to equal. Not say exactly equal, they must be able to equate. So for the first thing, you must make sure that S squared is equal to S squared. Now, if there is a 5 here, then you must normalize everything by 5 before you start comparing, right? So now here is S squared, good, S squared is clear. So now we need to compare this term and this term, right? The S term and the non-S term. So if I start by comparing the non-S term, so 3 must be equals to omega n squared, right? So that's why you have omega n squared equals to 3. So that implies that omega n squared will be equals to root 3, right? So straightforward. Now, for the S term, you would realize that we have 2 zeta omega n as must be equals to 2s, right? So I cancel away the s, which basically you have this. So if you rewrite the equation, zeta must be equals to 1 over root 3, which is 0.5774. In this case, confirm that it is an underdamped case, right? Remember, the whole timing diagram is for underdamped, right? So with this zeta and omega n value, we can plug it into the rise time formula, right? Rise time formula, and then plug in the zeta and omega n. You would be able to solve it to be 1.55 seconds for the first case. And then, of course, the settling time for 2% criteria will be 4 over zeta omega n. Again, you see, zeta is required, omega n is required, and zeta we already found, omega n also we found. So that basically gives us 4 seconds.
Again for steady state response for the system, cancelling S and 1 over S for U, S, and setting S equals 0 yields steady state's response to be equals to 1.
Okay, so the last part of the example 7 require us to find the steady state response, right? Now, steady state response, again, we use the final value theorem. We multiply the G by the input and then put a S here. So the input will be step function, which is 1 over S. Then S cancel with 1 over S. You basically have the Laplace, the final value theorem for S tends to 0 for G. Now, G is given by 3 over S squared plus 2S plus 3. So when S tends to 0, meaning that you put this term and this term equals to 0, you have 3 over 3. So the final steady state response will be the expression tending to 1.
For the system identification, we try to identify the system response by injecting a monostable pulse like input CO and wait for a response at the output PV. Process variable. Largely for most system it will fall within one of the two type of system response, and they are the self-regulating and the integrating response. FOPDT stands for first order plus dead time. First order indicates is a first order system, and dead time means between the start of CO trigger till PV response, where there is no action. Hence is term as dead time. For self-regulating PV, its steady states will follow that of the CO. If CO goes up, it will goes up. Likewise, if CO goes down, it will also goes down.
So this is, now we are going to system identification. We just finished the first and second order steady states error and steady states response, right? So now we move in a little bit more to cover the last part of today's lecture, which is the system identification. Now, in the real system, we usually inject some what we call the control output, which is a step function. Usually you use the step function. So by doing this, we have this process variable which we want to observe whether it responds together. This is basically the process variable, right? And then if you look at the step function comes up and go down, basically the process variable will follow through, right? Go up and then come down again. Now this type of response whereby it follows the CO, you basically call it a self-regulating, right? Basically, when it goes up, it will go up. When it comes down, it will come down. So with the input tracking the output, or CV tracking the so that this is what we call a self-regulating type. Now, why first order? Now, first order, if you look at this response here, for the step function, the response for the step function is basically like a first order equation. So therefore, we call this the first order. Now, plus date time. Why a date time? Now, in the real system, the output may not rise immediately at the point whereby the step function goes up, right? So therefore, there is a time delay. And this time delay is what we call the date time, whereby there is no activities and just waiting for the circuit response. So this date time. So this is a first order system plus by date time. And then, of course, is a self-regulating system. So it's FOPDT, first order plus date time, FOPDT, right? So that's how a first order plus date time looks like.
For FOPDT self-regulating, there are a few parameters to take note to construct the transfer function GP. S.
So basically, for first order plus date time, of course, we also have some parameters to look at. And this is pretty much similar to the first order equation that you studied, right? So in a first order response, but because this is plus date time, there's an additional term that I will caution you, right? So the key terms that we are going to study is the gain, and gain is defined by output, which is the process variable, O2 minus by O1 is output, right? Divided by input, which is the controller output, you call it the input, is I2 minus by I1. So it's actually output divided by input, which is your gain, right? So output O2 minus O1 divided by I2 over I1. So that's just a gain. It's the same as any gain, but we got to take the difference between the high and the low. Now, date time basically is a time measure from t T1 to T2. That means the delay from T1 to T2. So it's T2 minus by T1, right? Date time. This is a new term, of course. In your first order, there is no date time, right? In your first order expression, there's no date time. But time constant is already available in your first order system, right? First order system, you remember if the response rise up to 63%, the time taken from it from when it start at 0 to when it reach 63%, that is called the time constant tau. Now, same thing, this is also called the time constant, but we call it tau p, or rather it's T3 minus T2, right? So this is exactly the same. Okay. So with that, with this, all this defined, of course, again, the equation for PV, that means output over input, will be given by K tau P S plus 1, which is actually the first order response or first order equation, right? But because of there is a date time, which is theta P, then you got to shift the whole expression by e to the power minus theta PS. So this is indicating the shift e to the power minus theta PS. And that's basically the difference, the main difference between a first order plus date time and a first order system, because it has plus date time. And this e to the power minus theta P is the plus date time.
Firstly, the steady state's gain K will be the change of PV divided by change of CO. This changes of both CO and PV must be in percentage over percentage. For this case is O2 minus O1 over I2 minus I1. Second parameter is similar to the first order system we have went through. Lag time tal is taken at 63.2% of PV reaching final value. That is T3 minus T2. Final parameter, dead time as mentioned before, will be the idling time from the start of CO trigger till the first response of PV. This will be T2 minus by T1. Note that to construct GPS, lag time and dead time need to be converted to minutes.
So basically, this is as per what I have discussed or described in the previous slide, right? So, so the new thing is basically your date time. So date time raised to the power of e to the power minus theta p, and theta p is your date time, right? And other than that, you must be cautious about the units. Of course, inside the formula sheet, the units are specified, so you don't really have to worry. When you are doing the tutorial, refer to the units that is specified in the data sheet, then you won't go wrong, right?
This is the second type of PV response known as FOPDT integrating. As mentioned before, PV will not follow the steady states of CO. Here we see CO going up then down. However, PV only goes up and stuck at high. That is why we call it integrating. Output PV is like summing up everything under the curve, and hence it will not comes down and follow CO.
So now this is the second system. Again, it's first order plus date time, but now instead of self-regulating, we call it integrating. Now, why integrating? Because you look at the input CO, it goes up and down, but the output only goes up. It doesn't come down. So this is like something like summing the area under the curve, right? It doesn't go down. It always integrates up. Right? So therefore, this is why it's called an integrating function. Slightly different from the first order plus date time self-regulating. Right?
For FOPDT integrating, there are only two parameters to take note to construct the transfer function GPS. Firstly, the integrating gain KPI, and secondly, the dead time.
So for first order plus date time integrating, there's only two parameters to compute, right? And that's basically the integrating gain and the date time. Date time computation is exactly the same as the self-regulating. It's just the time taken for the idling. That means from T1 to T2. So basically it's T2 minus by T1, right? So this is the date time. So the date time is actually the same. But the integrating gain is slightly more complicated to compute. It's basically the outputs, it's basically the output slope divided by the input. Now, input is I2 divided by I1, right? I2 divided by I1, so this is input. Slope of the output is actually, or rather the gradient of output is actually O2 minus by O1 divided by T3 minus by T2, right? So this is a slope. So it's taking the slope of this guy divided by the difference in the input. So that's how the integrating gain is being computed.
First parameter. The integrating gain KPI is the gradient of the slope in PV divided by the change in input delta. CO. Second parameter dead time is the same as before, the idle time from the CO trigger to the PV response. For this case is T2 minus by T1. With dead time and integrating gain found, we can again construct GPS. Same as self-regulating. The KPI must be in percentage over percentage and dead time must be in minute.
As this is already described, again, same thing, your dead time will be involved in your e to the power minus theta ps because of this shifting function, right?
Please go through e-tutorial 12.
So this week we are going through 4 questions, which is question 6, which deals with Laplace inverse. Question 10 also deal with Laplace inverse and partial fraction. And of course, question 15 and 16, we deal with system identification. That is for the first order plus dead time, integrating and self-regulating. Okay, now let's take a look at the question. Let me stop sharing first. Let me stop sharing and go to the question for the tutorial. Okay, if you take a look at the question for tutorial 3, the first question.
Please go through e-tutorial 12.
For the first question that we are interested is basically question 6, right? Now, question 6 is related to question 5. So this basically using this question 5, they ask you to do the convert into the time domain. You know, question 5 is in the Laplace domain. They want you to convert into the time domain. So let's do it for 5 is a given, but you must fill up the detailed steps, right? Okay, let me set up my whiteboard and write the expression out. Now the first one, the first term, let me take a look, is 2 over 0.2s plus 0.5. So your first term is 2 over 0.2s plus 0.5. Plus 5 or plus 0.5? 0.5, yeah, 0.5. Now this is in your S domain. Let's say, for example, this is your G of S domain. Now, how do you take the Laplace inverse? First of all, Laplace inverse, you have to make sure you normalize the S part. So in order to normalize the S part, I need to make this S equals to S, right? So in order to do so, I got to divide the top and bottom by 0.2. So if I divide the top by 0.2, I will get 10, right? And then this one divided by 0.2, 0.2 divided by 0.2 will be 1, right? Then of course you got 0.5 divided by 0.2. So what do you get as a result of this? You get basically 10, right? 0.2 over 2 over 0.2. Let me double confirm. So you get 10 on top, 10 over S plus what? Plus 0.5 divided by 0.2. You get 2.5, right? Now you want to go change this guy back into GT. GT will be, of course, in time domain, you write it in a small letter. You'll be taking the Laplace inverse of Laplace inverse. Laplace is using this symbol. Inverse is minus of G of S, right? So you take a Laplace inverse of G of S. You basically do the Laplace inverse for 10 over S plus 2.5. Now 10 is a constant. We can take it out of the expression. So basically, you are looking at Laplace inverse of 1 over s plus 2.5. Right? Now, so we need to do a Laplace inverse for this form. So if we take a look at the formula sheet, let me see if I can find the formula sheet. And go to the Laplace table, right? Formula sheet. Okay, let me share with you the screen first before I go further. Let me share with you the screen for the formula sheet. Now, this is the formula sheet. If you scroll all the way to the bottom, you see the Laplace table, right? Now, we are moving from Laplace to time domain, right? So we are actually interested in this expression, 1 over s plus a. So after converting, you got e to the power minus at, right? So remember this, e to the power minus at. Now we go back to our solution. This is 1 over 1 e to the power minus at, right? So basically, let me rub away this accident. Basically, what we get here is, then we will have this basically equals to, then of course after Laplace inverse you will have e to the power minus 2.5. A is 2.5, yeah? T, right? So this is your time domain answer, g of t. So this is for part 1. This is 6 part 1. Now of course 6 part 2 we have another set of equation, which is, let me take a look first. 6 part 2 is 0.2 over 0.05 and 0.1. So the 6 part 2 is 0.2 over 0.05 s plus what? 0.1. Now same thing, we got to normalize this case. So 0.2 divided by 0.05, right? 0.2 divided by 0.05 for the top. And then of course this is 0.05 divided by 0.05, right? S plus by 0.1 divided by 0.05. 0.2 divided by 0.05 again is what? 0.2 divided by 0.05, you get 4. Right? So this you get 4 over S plus 0.1 divided by 0.05, you get 2, right? You get 2. Oh. So again, g of t will be Laplace inverse of your g of s, right? And of course, it's Laplace inverse of 4 over s plus 2. And we take out the common, the constant, so you got Laplace inverse of 1 over s plus 1, s plus 2. Applying the same Laplace formula, you got g of t is equals to 4 times by e to the power minus 2t. Okay, that's for part 2. So with that, we complete question 6, right? Now let's take a look at the second question that we are supposed to solve. That is question 10, right? Let's take a look at question 10 first, right? Let's go back to the tutorial and share. Now let's take a look at question 10. Now question 10 says that a system has this particular transfer function, output over input, determine the time response of a unit step function. So remember this equation, theta O out over in is 1 over s plus 2, right? So let's go back to the whiteboard. I will clear this, of course. If you want to refer back again, you can play back the video. There's no problem. So therefore, now let me write out the transfer function again. This is your theta out s over theta in s is equals to 1 over s plus 1 s plus 2, right? Now for this kind of function, again, of course, it says that if the input is a unit step response, so input is actually 1 over s, right? So they ask you to find what is theta naught, right? So of course, to find theta naught, first of all, you got to find theta naught s first, right? Theta naught s will be 1 over s plus 2, s plus 1, s plus 2, right? Multiply by theta 1s. Now theta 1s is already known as, this is 1 over s, right? So therefore it is 1 over s plus 1, s plus 2, right? So this is your theta s. Now before you do the actual partial, the Laplace inverse, you got to do a partial fraction first. So maybe I would equate this guy to basically a over s plus by b over s plus 1 plus by c over s plus 2, right? Now if I make the base again common, so for the first one, a over s, right? If I want to make to the common base, I need to multiply by s plus 1 and s plus 2. Since I multiply the bottom by s plus 1, s plus 2, the top I also must be multiplied by s plus 1, s plus 2. So if you cancel this and this, it go back this term, right? So similarly for b, the second term, b over s plus 1, right? So what is lack for the common is you lack of s, so you multiply by s, and then you lack of s plus 2, right? So it's s plus 2. So you have s plus 2 here. So if you cancel out these two, you get back the same expression, right? Now the third term, again, c is s plus 2, right? S plus 2, then your lack of s term and s plus 1. So on top, you also multiply by s plus 1. So that completes the whole thing. So because all of them are having the same denominator, you can add them up together. So basically, the numerator will become a s plus 1, s plus 2, right? Plus by b s plus 2, plus by cs s plus 1, right? Over your entire denominator, which is s plus 1, s plus 2. Now you take a look at this. This is equals to this, right? The denominator. So 1 must be equals to the whole expression here. So therefore, since the denominator is the same, the numerator must be the same. Right? So we can conclude that 1 must be equals to a s plus 1, s plus 2, plus by b s plus 2, and of course plus by cs s plus 1. Now, of course, if you try to equate and find out the expression, there is only 3 possible solutions. One of them is s equals to 0. The other one is s equals minus 1 and s equals minus 2. So 3 possible solutions: s equals to 0, s equals to minus 1, and s equals to minus 2, right? So you first of all plug in s equals to 0. This term equals to 0, this term equals to, because you multiply by 0, right? So then you are left with basically 1 equals to a, s equals to 0, so it's 0 plus 1, 0 plus 2, right? Then this 2 term already goes to 0 because s is here, 0, 0, right? So that is for when I substitute s equals to 0, right? So I'll get this. So it is basically 2a equals to 1. So this implies that a must be equals to 0.5. 2a is equals to 1, a must equal to 0.5. Now when s is equals to minus 1, s equals to minus 1, the second situation when s equals to minus, let me write slightly towards this side because it's too low, I cannot write. So you have 1 over 1 equals to, now when s equals to minus 1, which term disappear? This term disappear, right? Because this becomes 0, this whole term disappear. This term also disappear, right? Because minus 1 plus 1 is 0, this whole term equals 0. So basically you have b, left with b, right? B minus 1 plus 2. So this is again minus 1. So it B equals to 1. This implies that B equals to 1. So this is the case whereby S equals to minus 1. Right? Now, for the case of S equals to minus 2, then you have again same thing. 1 is equals to, now minus 2 plus 2, this guy is 0. So this whole term equals to 0. Minus 2 plus 2, this whole term again equals to 0. So you are left with C term, right? So you have C times by minus 2 plus 1, right? So you got minus 1 and minus 2, so it's 2, right? So again, C equals to 0.5. So with that solved, you will basically get this. So can I proceed from here? So your A is actually 0.5 over S, right? And B is actually what? B is actually 1 plus by 1 over S plus 1. And then C, of course, is 0.5, right? Plus by 0.5 over S plus 2. Did I got it correctly? Yeah. So this is basically your theta S, right? So maybe I should give some space here. So theta S, theta naught S is equals to this. So this is actually here, right? So now, in order to find the theta, which is small little theta t, we got to take the Laplace inverse of theta S, right? Theta naught S. This is S. So by taking Laplace inverse, we can Laplace inverse each of the term. This become 0.5, right? If you Laplace inverse S, you get 0.5, right? And then the Laplace inverse this, you get plus e to the power minus 1 minus t, and plus by 0.5 e to the power minus 2t. So that's your answer. Let me check if I got the answer correctly. Yeah, correct. So it's the same as the answer. So how? So this is for question 10, right? Question 10. Clear so far? Okay, question 10. Okay, I will just go straight without waiting for too long. I will just go straight to the next question, because if you are not very sure, you can again replay the video. Okay, next question we will be, let me share. Next question we will be doing question 15. Right, question 15 will be here, right? Now this is a what kind of process? Now first of all, you must identify the process. What kind of process? Now if your input change by a step, then the output change from one step and it stay. So it's following the output, right? But it's inverted. So this is basically FOPD, first order plus date time, because there's a plus date time. This is a first order, but it's an inverted first order. Now it's a self-regulating because it don't keep going down. So it actually is a self-regulating. It stopped there. This guy stopped, he also stopped. So therefore it's a first order plus date time self-regulating. So simple as that. So the first of them. Now the second one is they want you to find the date time, the lag time, and the process gain KP. Now, date time, quite straightforward, right? You look at this time, multiply, minus by this time, right? So you have this minus by this. So from the graph, they read it to be 0.17 hours. 0.17 hours. So that is your date time. And then lag time will be, which is your time constant, will be from the time, from this time when until it hit about 63%, you see that this is about 10 means that 2, 4, 6 about here. So when it reach about this point, you draw down the line and you check the time. So the difference in time as seen here is about 0.33 hours. So that is your lag time, right? Now for the gain, it will be the output, which is 100 minus by 90, which is 10, divided by the input. Input is actually 225 minus by 200, which is 25. So 10 divided by 25, right? So 10 divided by 25, you would have 0.4. 0.4 degree per hour per kilogram, right? Hour per kilogram. So it's basically this. The negative sign is because this is increasing and this is decreasing. Therefore, there's a negative sign, right? Or because it's an inverted relation. One is going up, one is going down. Now, so for the model, basically, you just plug in all the figures and of course the date time you put it here for the shift. So this is pretty straightforward, right? Pretty straightforward. Oh, so this question is no problem. But seriously speaking, I would say for if you look at the formula sheet, this guy, they have a requirement for in terms of minutes and hours. Let's take a look at the formula sheet. Let's take a look at the formula sheet. Okay. And I scroll to the first order plus date time. Let me see where is it. Of course, it's before PID. Yeah. No, this is PID already. Rise time, settling time. Here. Now, first order plus date time, self-regulating. So it mentions that the gain must be percentage over percentage, right? But sometimes you can't get percentage over percentage because for that particular question, there is no percentage over percentage, right? So you got no choice. Then in terms of this guy, time, the lag time and the date time, they need it to be in minutes. So this one you can convert. For example, just now that case, rightfully you should convert it into minutes, before you plug in, and not just plugging in straight away. So this guy must be in minutes, and this guy must be in minutes, rightfully. Okay. Now, the second part we are going to look at is basically the question 16, right? Again, question 16 is another kind of system. Now, as you could have probably guessed, we would try to do first order plus date time, but this time around is an integrating process. Why do we say it's integrating? Because you see, in my step function plus date time, it goes up, right? But when it comes down, it never stops. It continue going up, right? And then at a certain point, it sloped down again, right? So this is basically first order plus date time integrating process. So that's the question. Now determine the process parameter. Now process parameter, date time there is two of them. So you have one date time here, right? One date time here and one date time here. So in order for you to find, you got to take the average of the two date time. So first date time, you compute. That means you measure from here. Maybe it's about 34 minus by 31. You get 3 seconds. 3 minutes. And then this here is about 14 minus by 12. You got 2 minutes. 2 minutes and 3 minutes. You add together, divide by 2. So it's about 2 point something minutes, 2.5 minutes. So the average date time is about 2.5 minutes. Right? So it's quite straightforward for date time. Now for gain, as we know, it's the slope, right? Slope divided by the input changes, right? Now, what is this slope here? This slope here is actually, you can take 34 minus by 14. That is the upward. And then, of course, this is about 70 minus by 40. So 34 minus by 14, you get 34 minus by 14, you get 20, right? So the y you get 20. Now the x you get 20 and y you get 70 minus by 40, which is 30. So 30 over 20. So you get the first one, you get 30 divided by 20. That is 1.5, right? 1.5, the slope of 1.5. But again, you have to divide by the input. Input is 40. Sorry. Input is percentage over percentage. So this is about 68%. Minus by 60%, about 68 minus 60, so it's about 8%. So you divide by 8. So you get the first one, you get about 0.1875. So let me write down somewhere. Let's say we go back to the board and then we clear this guy. Okay. So the first slope, we get we get 70, 40, right? So here's on top here is 70, below here is 40, right? And of course, this guy here, you got 34. And what you get here is 14. Right? So the slope really is actually equals to 70 minus by 40 divided by 34 minus by 14. So you get 30 over 20, right? So it's actually 1.5. Right? But the input changes. Input change how much? Input changes from. Of course, this is the slope. The slope goes up. The input changes from this value to another value, right? To another value. And the two value are, if I read from the scale correctly, the two value are 68 and 60. So here is 68 and here is 60, right? So you got to divide by so the gain pi is actually slope divided by input, right? Input change. Input change is 68 minus by 60. So it's actually 8. So it's 1.5 divided by 8, which gives you about 0.1875 unit later than I fill in. So there's the first slope, right? First slope. Now, of course, there is another slope whereby it's sloped down. Sloped down to where? Let me check. Where it's sloped down from. Okay, so it's sloped down from this point and all the way down, right? Let me erase the part. Oh gosh, it erased everything. So I continue the slope here. So now the second slope is slope to here. Of course, if you look at it, it is about 40, 50, maybe about 44. So this point is about 44. It's slope from negative to 44. Here is 44. Then of course your x is from 34 to 50. So this is 34 and here is 50. Right? So the other slope will be slope here, will be a negative slope. So it's actually 40 equals to 44 minus by 70, right? And over what we call 50 over 34. So at the end of it, you get an answer which is 70 minus by 44, you get minus 26 on top. And bottom, you get 50 minus by 34, you get 16 below. So the second slope is actually 6 divided by 16, which give you minus 1.625, right? So the second KPI, KP integrating, will be your slope again, minus 1.625 divided by the input. Now the input also changes much lower, right? The input also changes much lower. Let me check the level. This level is at 50. So this is at 50. So the input actually changes from 68 to 50, right? But it's also in the negative sense. So therefore, it rightfully is minus 60 plus 50. So what you get here is this divided by 18, right? divided by 18. So it is actually, the answer is 0.0903. Right? So you got the first one as this one, second one as this one. So you take the average of the two, so you plus by the top one, 0.1875, and you divide by 2. So your average KPI will be, this is the average, will be 0.139. 0.139. Oh, so this is your average KPI. Okay, so with that, let me go back to see whether we get exactly what the, okay, it's about there. It's about there. I think so. Let me see. Let me check again. Is it about there? 0.139. And your answer is 193 and 139. So maybe you can counter check for me, but the idea is basically like that, to get the KP average and KPI average and the date time, and then you plug in the expression here to get your transfer function. And that's basically it for tutorials question 16. So this is basically, that's basically it. So now you are seeing which screen? Let me see. Let me stop share again. So basically, with that, we conclude today's lesson, and wish you all the best. Thank you.